All right, section 1.2, we're going to encounter the actual first item that's truly calculus. And if you haven't had calculus before, you probably have never seen this idea before at all. All right? This is the concept of a limit. So generally speaking, a limit is simply a y value that you get really close to, and you may or may not actually arrive at that value. So something you get really, really close to and you may or may not actually arrive at. And there's some notation issues that you have to be aware of as you're working through this idea. This is the notation where it has the lim, and it's got values down here on the bottom. It looks like there's this arrow stuff. That f of x, that's notation that should look familiar to you. That's just function notation. And this right here, all of this information actually is read as this. That's how we read it. So when I see that notation that's circled there, I read that as the limit of f of x as x approaches the number 3, because that's what the value on the bottom is. And that plus sign after the 3 means from the right. And if you think about a number line or a xy axis, the right side's the positive side and the left side's the negative side. So that's a reasonable sort of a description or viewing of how that goes. So this is 3 from the right. And for the same reason, now when we have the image down here that's got this negative here, that is thought of as 3 from the left. That is the negative side of the graph. And when there isn't any plus or minus after the 3 like there is on the bottom, we just say that x approaches 3. And what we mean is it approaches 3 from both sides, from the left and from the right. So this is the notation for that idea. And I realize we haven't actually looked at one, but we're about to. So is everybody good with this? Okay. In order for a limit to exist, it will exist if and only if both corresponding one-sided limits exist and are equal. So jot that down, and I'm going to go back to the previous slide to talk about those limit notations again. So it exists if and only if the one-sided limits exist and are equal. So that existence definition is talking about this piece down here. This limit, as x approaches 3, is only going to exist if each one of these existed and if they were the same. That's what that's saying. This one's only going to happen if these both match. Okay? Now we're going to actually do one, and all of this will sort of start to come together, I'm hoping. All right, so this image should look like the same image, or fairly close anyway to what's in your notes. Does it look okay? Yeah. All right. So the idea of limits is you're approaching a specific value. So we're going to take the first one that's asked for here, the limit as x approaches -1 from the right. So the first thing is x being -1 is right here, right? This is -1. So if we're on the right-hand side of -1, we are on this side of the graph somewhere. So far, so good? But you have to be on the graph, that is, on the curve. So if we're on this side of -1, we have to be up here on this piece, because this is the piece of the graph that's on that side of the graph. This is the piece of the equation that's on that side of the graph. Let's say it that way. So we're over here somewhere, and it doesn't really matter where you want to say you are to start with. You just need to be over there somewhere. Okay?
Wait, Dr. Hand, does that just mean a quadrant 1 somewhere?
It doesn't have to be quadrant 1. It just needs to be on the right-hand side of whatever value you're looking at. So I could have chosen, Hannah, to put the point right here and be in quadrant 2 instead, and that'd be fine.
Like all the positive values are
It could be on the negative values. We just don't happen to have any on this graph. Like, let's say instead that this piece we're down here, right? Same thing, just, down here instead. We would simply have started down here because that's on the right-hand side of the value x equals -1. Okay, so it doesn't matter whether it's a positive y value or a negative y value. It just means that the x value is bigger than the one you started with. Okay? All right, so I put my red dot here to begin with. So we're on the right-hand side of where x is equal to 1, and our goal is to get close to x equals 1. So imagine that you're now standing on the red dot. Which direction are you going to move if you're going to walk along that curve towards x equal -1? You're going to walk left, aren't you? So you're going to walk along the curve in the direction that my arrows are pointing. So you've got your little stick figure guy, and he's walking along the curve. He's supposed to be walking along the curve in this direction. Is everybody picturing what's happening? All right. Now, he's walking toward a hole in the graph, which means he can't ever actually arrive at the hole because that hole is empty. And that's something that's a little bit different. But the question is, where is that hole located? That is, what y value are we getting close to? And the y value is 2. So this limit is 2. A limit is a y value that you get close to that you may or may not ever arrive at. So as we're tracing along this curve, the y value that I'm getting ever and ever and ever close to is this hole in the graph. Because there's a hole in the graph, I don't actually arrive there. But that's okay, because that's not what the question asks. The question asks sort of what's in my intent, where am I headed? Are we all good with that one?
Does it matter what point you pick for the red dot?
No,
Okay.
because you're still going to be moving left. That's why the red dot didn't actually matter. It just mattered that we were over on that side of the graph. Okay? All right, the next one then is for part B, is still approaching -1, but what does this one say? From the left, which means I need to be somewhere on that side of the point -1 to start with. Again, it doesn't really matter where. I'm going to use green this time, but my green dot's going to be somewhere to the left of the -1. But again, I'm supposed to be approaching -1, which means if I'm standing on top of my green dot, which direction am I headed? Right. So we're going in this direction. Now we're actually going towards a closed dot in this case. It doesn't really matter, because it doesn't really matter whether we arrive there or not, right? We had an open dot last time. But we are still headed there. The intent is, what y value would I be at if I actually arrived at that black dot? It's a y value of 1. So this limit is the value 1. All good? Part C. What in the world is part C asking? From both sides. So now imagine that you've got two people, one on the green dot and one on the red dot, and they are walking along the curve. Okay? The only way that the limit exists is if the two people actually arrive at the same location. That is, they're headed to the same location. Let's say it that way. Are these two people headed to the same location? No. One of them is going to get close to the point 2, y value 2. The other one is getting close to the point, or the y value of 1. They're not going to see each other. They're going to miss each other entirely, right? They're not arriving or even getting close to the same location. When that happens, we would say that this limit does not exist, and an abbreviation that you will see often used for that is D&E.
So we can use D&E?
You definitely can. Yeah, D&E is good. So this does not exist. This limit doesn't exist because the two one-sided limits weren't equal. And that's actually what this limit existence definition said a moment ago. This limit can't exist because while these both are, it says, they both exist, the problem that we're running into is they're not the same. All right, we're going to do a couple more. Let me clear out my picture so that we can talk about the other two. This next one actually says that we want the limit as x approaches where? -2, I think, right? Okay, good. Make sure the picture, your picture and mine say the same thing. -2. How? From both sides. So again, if I want to, I can take a red dot and I can take a blue dot, or I use using green, a green dot. So here's -2. I need to be on the left-hand side of -2 and on the right-hand side of -2. Okay? So here's my left-hand side of -2. And again, I'm going to start over here just because we did before. Here's my right-hand side of -2. All good so far? Okay, green dot. He's tracing along towards x equal -2. What value is he getting close to for a y value? 1, right? He's still tracking along the curve where he's getting close to a y value of 1. In fact, he's at a y value of 1 the whole time, but he's still getting close to a y value of 1. This red dot's a little interesting, right? Because for a while, it's tracking along this curve, but we still have to keep getting close to the x value of -2, which means all it does is it jumps down here, and then it keeps going left. It's just going to keep going left. I don't care what happens to the curve and whatever it goes, it just keeps going along whatever curve exists. So the red dot is doing something like this. And it'll jump down here, and then it's going over here. So that red dot is getting close to the y value of, the x value is -2, the y value of 1. Right? This is a y value of 1. The red dot traces along here, and then it jumps down and it keeps going. It's still approaching a y value of +1. Are you guys okay with that? So from both directions, even though we had to make this jump down, from both directions we still get close to the same location, the exact same place, right? So that limit actually exists because it's the same from both directions. What matters is what happens when we get really close to the x value we're concerned with, in this case the x value of 2. -2, yeah, -2, which gives me a y value of 1. Okay, we're going to do the same kind of an argument one more time, except that our point that we're looking at is an x value of 0. Where is the x value of 0? It's what? We are going to come at it from both sides. Where is the x value of 0 located?
Between 2 and 3. Of 1. Oh, wait, what do you mean?
I think I'm asking a question that's not making sense.
Yeah.
It's the what? It's going to be not the x-axis, but it's the y-axis actually, right? It's actually the y-axis. So, right, so this is x equal -1 on the left, and this is x equal +1 on the right. X equals 0 could be the origin. In this case, that's not where my graph is, so my x value of 0 is actually located up here somewhere. But the x value of 0 is somewhere along the y-axis, right? Okay. But just like Micaiah said, we're going to be approaching that x value from both directions because there's not a positive or a negative after the 0, right? So we're going to put a red dot on the right. I'm going to put a green dot on the left. And we're going to move toward the value. Now the green dot has to make the jump this time. Okay? It jumps up here to the open circle, and then it keeps going. The red dot just keeps moving to the left. What value are they both getting close to, approximately? Because this graph's not precise. Give me an estimate. What do you think? 2.8. Is that okay with everybody? 2.8, 2.7, 2.5? I don't know, somewhere in there. We'll go with 2.8. So this is approximately. If it bothers you to put the equal sign, you can say approximately because we are approximating with this particular graph. It's approximately 2.8. And they're both approaching the same location, right? I agree one of them had to make a jump. That really doesn't matter. What matters is as they get really close to that x value, that they're getting close to the same y value. Okay? That's what a limit is. A limit is a y value you get close to. Sometimes you arrive there and sometimes you don't. Now, we're going to take a look at another one. It's a little different because there's not a graph given to us, but we do have an equation given to us. So we're going to look at the graph of this equation in part, but we're also going to look at numerical evidences of what happens here. So the directions say use numerical and graphical evidence to conjecture. That means to guess. It's a fancy word for guess, but it means like guess with a substantiated reason. That's what conjecture means. Whether the limit exists, number one, does it exist? And number two, what in the world is it, if it really does exist? Okay, so there's two things you have to do. Notice, if the limit doesn't exist, you don't have to do anything else, right? I mean, you're going to do the same amount of work either way, but you won't have a second answer, I guess is my point. Okay? All right, so let's take a look at this. you know what, grab your calculators and let's graph it first. Take a look at the graph. Tell me what you see when you graph this. Make sure when you're putting this in your calculator that you're making sure that all of this is in the numerator and all of this is in the denominator. So that might mean parentheses on your graph. You have parentheses around everything on top, parentheses around everything on bottom, depending on how your calculator is set up. The limit part at the beginning is not what we're focusing on at the moment. We're just looking at a graph, okay? What's it look like? Visually, what's the picture sort of look like to you? It looks like a line. Actually, it really is a line, too. And there's a very good reason why. And it has to do with the fact that if we were to actually reduce this equation, right, if we were to factor in the numerator, it would actually cancel out with what's in the denominator. That's why that's happening. You remember that from algebra. But this actually is a line, and the line looks something like this. And if you look carefully, it's crossing at a value of 3. Now, that's not because this says x approaches 3, because that value where it crosses at 3 is not an x value, right? That's actually a y value there. It just happens to be the same as the limit that we're approaching. So the x value we're concerned with is something over here, something around this location. What's happening there is the question. So what I'd like for us to do next is I'd like for you to look at your table, okay? Now we're going to look at the table from the same point of view that we did last time. That is, if we're approaching a value of 3, it means I need to have values close to 3 and slightly on either side of 3. This is like that pi over 4 example we just did in the last section, right? So a value close to 3, for example, slightly smaller, might be 2.9. And then if you remember what we did on that example from last time, I did something like 2.99 next. And what do you think I might do after that? Yeah, 2.999. And your calculator will deal with all of that just fine. And then on the flip side, on the other side of this, so this is actually values that are slightly smaller. So what we're actually doing in this column right here is we're finding the limit as x approaches the value of 3 from the left-hand side. That's what we're doing. These are values slightly smaller or to the left side of that value 3. But I need to do it from the other side as well. So from the other side means values slightly larger than 3. So maybe 3.1, 3.01, and 3.001. And these again would be values that are the limit as x approaches 3 from the right-hand side. And the table is set up exactly on purpose the way that it is, because as you go down the table, you're getting ever closer to the value 3. Right? You're moving along the curve in the right direction. You're following that arrow like we did in the picture. Now you're going to get f of x values. Your calculator is going to give them to you. So somebody go through and tell me everything you got on the 2.9, 2.99, and 2.999. Give me those 3.
5.9.
Go ahead. Uh-huh.
5.999.
Good. Somebody else give me the values you had on the other side, the 3.1s and so forth.
6.1, 6.01, 6.001.
All right. What y value are we getting close to, guys? 6. We're getting close to 6. Now, the answer then here is 6, because this value is getting close to 6 from the left, this value is getting close to 6 from the right, and those two match. So the limit is 6. Now over here, the reason that's happening is because if you were to actually reduce this, and we're going to get into that next class, this equation would actually reduce to y equals x plus 6. I'm sorry, x plus 3. And then if you were to put a 3 into this, 3 plus 3 is 6. Now here's something interesting for you. I want you to take that screen that you have on that calculator and I want you to put in 3. that numerical table, put in 3. What's your calculator say? Error. Why? Because what? It doesn't get there. That's exactly right. Why not?
You get 0 over 0.
You would have a 0 over 0. If you plugged 3 into this equation that you were originally given, you'd have a 0 in the denominator. That's not okay. Your calculator can't deal with that. What's really happening in the graph is there's a hole there. Do you remember that from algebra? When this happens, there's a hole in the graph. That's all right. The limit still exists. The function doesn't exist there, but the limit does. Well, if you were actually drawing this by hand, it would do this. You'd have a hole in the graph, and that height of that hole would be at 6.
Oh, okay.
Yeah, your calculator has, it's pixelated, right? I mean, it can't show a hole. And to be honest, the hole's not got any width or depth because it's a single point, and points don't have any dimension either. So it can't show the hole. But this is the visual way that we sort of draw when we draw a hole in the graph. All right. This one would be the same. The table would be set up the same, but the result's going to be quite different. All right? We will pick up with this one next time so that we can see that result and how that affects it.